Hello, everybody. Mr. Lake here. Welcome to Math Boot Camp. In this video, we're going to be talking about significant figures. What does that mean? What are significant figures? And how do you know how many significant figures a number has? Let's get started. So, in science, numbers generally are measurements. It's data, right? When we're working with scientific information, we're usually working with data. And that data came from taking measurements. When you take a measurement of something, you're using a tool, and tools only have so much accuracy that they can represent. So there are really crude tools that you could use to measure things, but you wouldn't be able to measure it very accurately. And then there are extremely precise tools that you could use to measure something with a very high level of accuracy. And this element of taking measurements is actually represented in the numbers that you get from your measurements. So, and that's where significant figures comes in. Significant figures is a representation of the accuracy of measurement. And it's a way for us to keep track and to maintain the accuracy of our measurements as we go through manipulating numbers using math. If that was all like, if none of that made sense, just stick with me. I think after we start going through some examples, things will start making a little bit more sense. But in general, when you take a measurement of something, you generally measure all of the digits you know plus one more digit that you estimate. And so significant figures for a number includes all known digits plus one estimated digit. I'll give you an example. Let's measure this gray rectangle up here. We'll call it a pencil. Let's call this thing a pencil. We're using a centimeter ruler to measure this pencil. Now, here's what we can see. We can see very clearly that the pencil goes beyond the 5 centimeter mark, right? Now, it also very clearly goes beyond the 5.2 centimeter mark. So we know for sure, 100%, this pencil is at least 5.2 centimeters long. But it doesn't end perfectly on the 0.2 centimeter mark. It goes a little bit beyond it, right? And here's where estimation comes into play because it goes beyond 0.2, but it doesn't get to 0.3. But there's no lines in between here that are going to help us to decide exactly how far it goes. So we have to estimate. We can't just say, oh, we're going to ignore that. And we have to estimate. It looks like it's about a third of the way between 0.2 and 0.3. So let's say that this measurement, this pencil is 5.23 centimeters long. That measurement includes everything we know, the 5.2, plus one digit of estimation, the 0.03. That was just a really quick example to kind of show you what the idea behind significant figures is and where that concept even comes from or where it might come into play. Like why we have to. The question I always get from students is, why do we have to relearn how to use numbers? And it's because that you may have learned how to manipulate numbers just for the skill of manipulating numbers. But now you have to manipulate numbers and you have to maintain accuracy. You can't, as you add numbers together, if you add two measurements, the result that you get can't suddenly be more accurate than the measurements that you took, right? Does that make sense? No one is here, so no one is able to answer that question, but I hope that makes sense. But here's what you really want to know as a chemistry student, right? You're like, okay, where does this apply to things I'm going to have to do in class and on tests? And, what's the skill that I have to be able to actually use? So here's where we get into that. The first thing you need to be able to do is identify how many significant figures are in a number. There's 5 rules, and I would write these down. Rule number 1 is that when you look at a number, anything that is not a 0 is significant. So for example, in the number 72.3, the 7, the 2, and the 3, none of those are zeros. And so therefore, they are all significant. Therefore, this number has 3 significant figures. Rule number 2. Here's where things get a little more complicated. Zeros are tricky. Any zeros that are between non-zero digits are always significant. So in the number 70.2, the 7 and the 2 are significant because they're not a zero. And then that zero between them is significant because it's between them. It's a sandwich zero. And so this number has 3 significant figures. The number 700.2, the 7 and the 2, of course, are significant. And both of the sandwich zeros are significant. It doesn't matter how many zeros are between your non-zero digits. All sandwich zeros are significant. And this is where things are going to mess people up the most. Rule number 3 is the rule that most people have trouble with, and it's the trailing zeros. Trailing zeros are significant sometimes. It depends on whether there's a decimal point in the number. If a decimal is present, it makes trailing zeros significant. And that includes trailing zeros that are before and after the decimal point that we're talking about. So let me give you a couple examples. I'm going to get out my drawing tools here so I can help you out. So in the number 72.00, the 7 and the 2 are significant. Now, these are trailing zeros, and so we have to ask, is there a decimal in the number? Yes, there is. Therefore, they are significant. So there's 4 sig figs here. But what if the number was 7,200? Well, in that case, the 7 and the 2 are still significant. But these 2 zeros, these are trailing zeros. There's no decimal in this number. And so they are not significant. This only has 2 sig figs, which, if you haven't caught on, is the abbreviation for significant figures. What if the number was 7,200.0? Now the 7 and the 2 are significant. And because there's a decimal, all trailing zeros, including ones before the decimal, are significant. This number has 5 significant figures. Now you might be thinking, wait a second, those are the same number. How is 7,200 and 7,200.0? How is there any difference between them? Well, it has to do with the accuracy that they portray. This number says we know for sure that the number is 7,200, and we know accurately to this digit right here. This number says we know that measurement accurately to this digit. We know that it is exactly 7,200.0. It's not 7,201 or 7,205. There's no question. We know the accuracy to this place, whereas this says we know the accuracy to this place. So they are the same value, but this is a much more accurate number than this number. And this is kind of maybe a concept that is new in mathematics, that, where the way that you represent a number, like, changes the claim that you're making with that number. But that's what we've got to think about in science. Because what if you could only measure something accurately to the 100 meters or something like that? Then you could only represent that number as 7,200. But if you can measure accurately to the 10th of a meter, then you could represent that number as 7,200.0. Again, if I'm still not making a lot of sense, we'll do more examples and things will fall into place for you. The type of zeros that we haven't talked about yet are leading zeros, meaning zeros that occur at the beginning of a number before any non-zero digits. They are never significant, even if there's a decimal in the number. For example, let's say we had the number 0.0072. Looking at this number, the 7 and the 2 are, of course, significant. These leading zeros are not, right? These are zeros at the beginning of a number. They are what we call placeholder zeros. They're not significant. So this only has 2 sig figs. One more rule you should be aware of: counting numbers and defined constants have infinite significant figures. Let me explain what I mean here. So let's say your dog had puppies and you were like, she had 8 puppies. That is a counting number, right? You sat there and you went 1, 2, 3, 4, 5, 6, 7, 8. There are 8 puppies. There's no question about whether there's 8.1 puppies or maybe there's only 7.97 puppies. No, there's 8 puppies, right? You counted them. So when you count something by whole numbers, we don't say that only has one significant figure. We would say that has infinite significant figures because there's no question about how accurate that number is. It's a counting number. It's a whole number. So the rules of significant figures don't really apply. Same for defined constants and defined conversion factors. So like when we say there's 60 seconds in 1 minute, there's 60 seconds in 1 minute. There's not 59.8. There's not 60.002. There are 60 seconds in 1 minute. That is a definition within our mathematical and measurement system. And so we say that has infinite sig figs, or the rules of sig figs don't apply. Now, what you might have picked up on is that the rules of significant figures basically are anything that's not a zero is significant, and then zeros are the problem children. They are the ones that make it difficult for us and that we have to think about. Leading zeros, but it can all be simplified into these 3 rules. Leading zeros are never significant. Sandwich zeros are always significant. And trailing zeros are sometimes significant if there is a decimal point. It really all comes down to that. And of course, counting numbers or defined constants, they don't have any specifics. And there you have it. That is the end of this video. I hope that that was helpful to all of you, and I will see you in the next video. But until then, take care and have a good one.